At lesson 6 in the instruction book on page 52, this is our first lesson in unit 2. Now, the book is a little wishy-washy on which lesson it wants to teach you what. So it's going to give you a little bit of stuff in this lesson that we're not actually covering until the next lesson. So we're just going to bear with them and do the best that we can. What is a function? A teacher likes to remind his students that their future earnings are often a function of what they have learned, or what they're learning. What exactly does it mean to say that one thing is a function of another? It relates to dependence. Another way to present the idea above is what you are paid depends on what you know. In mathematics, a function is a rule that defines a dependent relationship. Now, you should have this on your graphic organizer already. A function is a rule that defines a dependent relationship. A function creates exactly one output or result for each input. The diagram below shows the function add 2. The input is 3. The function says add 2, and the output is 5. Now, if you're thinking about what we did this morning, the input was our batter, our waffle mix. The function was the waffle maker, the waffle iron. And its function was to add heat to that batter, which causes it to change forms. In this function, you take your input, which is 3, then you add 2. The operation is adding 2. And then the output is 5. Of course, with our waffle maker, our output was waffles. Remember that the function is like the machine. It tells you what to do to the input. This function, we're just adding 2. There is only one possible output for each input. The function add 2 is expressed in words. It can also be written as the equation y equals x plus 2. Or the input plus 2 is equal to the output. And remember that plus 2 is the function. It's what is happening to the input. So what are some relationships that are a function? Each coin of American currency is assigned one specific value in dollars. For example, the value of a penny is always $0.01. In this function, an ordered pair relates the name of the coin and the value in dollars. So the input is penny, its value is 1 cent. The input is a nickel, its value is 5 cents. Now, nothing is happening to the penny or the nickel or the dime. We're just saying that these two have a relationship. Because it is a penny, it is worth 1 cent. Because it is a dime, it is worth 10 cents. Most mathematical functions include ordered pairs of numbers. For example, a 120-pound person burns about 65 calories per mile while walking. The table shows how many calories the person would burn walking different numbers of miles. Okay? The input is the number of miles. If they walk 1 mile, they burn 65 calories. If they walk 2 miles, they're going to burn 130 calories. 3 miles is 195. The input is the number of miles walked. The rule is to multiply the number of miles by 65. So your function is multiplying by 65. And then, of course, the output is the number of calories burned. Input is your x's, output is your y's. The function is the operation you're performing, which is multiplying by 65. What are some relationships that are not functions? A basketball coach gives the starting players a game jersey. At the same time, he measured the players' heights. This relationship is a function. For each jersey number, he records only one player's height. If jersey number is the input and height is the output, then the relationship is a function. Think about your inputs. The input is the jersey number. Any of you that have ever played on a team should know that you cannot have multiple players with the same jersey number. Okay, that's your identifier. That's how the announcers know which player you are. It's by your number. So this one is going to be a function because there's no opportunity for those inputs to repeat. You're just going to use each jersey number one time. And every player on the team could be the same height. That doesn't matter. But if we reverse the relationship, what if player height is the input and jersey number is the output? The diagram below helps you to see when the input is 68. The output may be either 10 or 18. This is not a function. In a function, one input can have only one output. Guys, think about it. If we are just lining our team up by their height, is it possible for two players to be the same height? It is possible. Okay, it happens a lot. Now, we can't give them the same jersey number just because they're the same height. They're different players. They need different jersey numbers. So we have the potential for one height to have multiple jersey numbers, and that is exactly what's happened here. We had two 68-inch players, and we had to give them two different jersey numbers. Because we have one input with multiple outputs, this is not a function. Do the data in this table show a function? If you switch the input and output values, is it a function? So if we look through the table as it is, remember the inputs are the X, outputs are the Y. We've got 3 being repeated, and we have 5 being repeated. Because they are repeats, we have to check their output. If they have the same input with different outputs, it is not a function. We have 3 being paired with -3 and +2. That alone tells us this is not a function. The 5s also have multiple outputs, which would again cause this to not be a function. Now they want us to reverse it. Just flip-flop the X's and the Y's. So this time, I'm going to rewrite it. My inputs are going to be the original outputs. So -3, 2, 4, 5, and 6. And my outputs will be the original inputs. 3, 3, 5, 5, and 6. Now when we look through this table, we're looking for duplicated X's just like before. Remember, the inputs are the X's, the Y's are the outputs. We switched them. So I have -3, +2, +4, +5, +6. None of my X's were repeated, so we know that this is a function. Okay, none of the X's were repeated, so there was no opportunity for duplicate inputs and outputs. It doesn't matter. Every output could be exactly the same. Okay, the outputs don't matter. If all of the inputs are different, the outputs do not matter. They only matter if we have duplicated inputs. All right, plot the ordered pairs from each table to represent the relationships as graphs and then answer the problems. Number 2 says the table below shows the number of dog licenses issued in the town of Palmer over a 5-year period. On the blank graph to the right, label and number the axes and then plot the ordered pairs. Now, on your video, I told you when you are making a graph, you have got to label your axes and give them increments. Now, my x-axis is going to be for my inputs, and my x-axis is always horizontal. So my x's are going to go along that horizontal axis. Now, I need to number those. I have to show 5. I've got 10 lines here. 0 is going to go in the corner. I could go 1, 2, 3, 4, 5, 6, all the way through 10. Since I only need to show 5, I'm going to go every other one. There's 1, 2, 3, 4, 5. As long as you space them evenly, it does not matter how much you spread them out. Just make sure all your data fits. Now, my y-axis is the vertical axis, and that's where I'm going to put my outputs. Now I've got to go all the way to 150. I can space these however I want to make them fit. I've got 10 lines going through here, so I have to go to 150. If I divide 150 by 10, it tells me how many I need on each of these lines. It gives me 15. So I would have 15, 30, 45, 60, 75, 90, 105, 120, 135, and 150. Now my graph shows me the increments. It has everything numbered and covers my whole table. The only thing left to do is to label. My x-axis is the year, and my y-axis is the number of dog licenses sold. Now, when I plot my ordered pairs, I'm going to start with X. 1 year, the first year, I sold 75. So I would go to 1 on the x-axis, 1 for year, and 75 for licenses. The second year, which would be year 2, it was 100. So I'm going to go, there's 90. I'm going to go 2/3 of the way up. The third year, it was 125. So I'm going to go up to here. The fourth year, we sold 125 again. And then the fifth year, it was 150. Does this graph pass the vertical line test? If I took my pencil and passed it across the graph, I can only touch 1 point at a time. I'm good here, I'm good here, 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 and here. So this would be a function. Describe the relationship between the input and output values. Each year, they sold a number of dog license. Now, I don't want to be too specific. Okay, we're just describing the relationship. Each year, we sold a certain number of dog licenses. Number 4 says that dogs age faster than humans do. Some people claim that dog years are a function of human years, as shown in the table. On the blank graph to the right, label and number the axes and then plot the ordered pairs. Now again, I need to get my x's on my x-axis. Okay, the inputs are my x's. And again, I just have to make it through 5. So I'm going to zeros in the corner. 1, 2, 3, 4, 5. And that's going to be age in human years. Now on my y-axis, I've got to get my age in dog years, or my outputs, and I have to make it to 35. Now 35 divided by 10 is 3.5. I don't want to count by 3s. I want to count by 5s. It's okay to go up because I'll just have extra room. So 5, 10, 15, 20, 25, 30, 35, 40. And that covers all of my data, so I know it'll fit. Now when I plot my points, I've got 1, 7, 2, 14, 3, and 21, 4, and 28, 5, and 35. Now the question would be, will this pass the vertical line test? And the answer, of course, is yes. If you take your pencil, you are only touching 1 dot at a time, so it's a function. Describe the relationship between the input and the output. If you're looking for a pattern here, each human year is 7 dog years. Each human year is 7 dog years. Look for the pattern. 7, 14, 21, 28, 35. You're multiplying by 7 each time.